Welcome to this presentation about the development of a 2-axis CSP concentrator with integrated thermal storage. This project is made by me, Stefan Larsson Mastonstråle, working at Maston Renewable Energy Laboratory in Sweden. And we have been working in collaboration with Loughborough University in UK and a few other parties. We've been working with the solar concentrator with Cassegrain optics. We evaluated a number of reflector materials and manufacturing methods and different optical geometries to enable a high temperature operation of around 1300 degrees in the receiver, and finally selected 8 different Cassegrain geometries to use. We also achieved good performance in the theoretical simulations, and experiments was also indicating promising results, but was very sensitive to mirror surface roughness. And at this high concentrating ratio, it's evident that using some high need of very flat and correct curvature mirrors of less than 2 milliradians in surface roughness. And this is very demanding to make in real life. In the first concentrator, we used the honeycomb method to stack very thin glasses of silver mirrors on top of aluminium honeycomb, and casting these in a casting mold similar to automotive industry casting of body parts. This method works quite well to do, and is maybe promising to do in industry. We also worked a lot with the method to limit the emittance losses in the solar receiver and to have high absorption ratio to emission ratio in these high temperatures, which is also very demanding, as there's very few materials that can actually operate at these high temperatures. In the simulations of the optics, we could see also quite interesting results that may be achieved, but this was made in the total system in simulations. The other part that we were working was to create solutions of heat transfer ducts that was made in ceramic part and ceramic insulation, and also designed to be able to manage a hot gas transfer from the solar concentrator to the energy storage and to a heat engine that is operated to produce electric power. So the system stores solar thermal heat into the storage in one step and then transfers that into a heat engine and produce electric power 24/7, day and night time, up to a certain number of operational hours per day. The heat storage itself was made with a PCM metal alloy that in this project was doing tests of achieving a different phase change temperature than some other published projects. It was also a lot of work working with how the heat transfer can be made. The storage media heat transfer was between the different system parts was made via hot gas heat transfer, and it also was clearly visible that the gas mass flow rate is very important to achieve a good operation of the engine. But it's also a good means to be able to throttle the engine power up and down in the system. The simulations of the engine was produced in transit simulations to see the actual phase change behavior, including the heat transfer rates of the heat exchange surface areas and the total combination of the system heat losses. the heat losses need to be reduced quite a lot in this type of systems, and several different routes was tested in physical experiments to see how to reduce the thermal losses, so they may be possible to get down below 10% of the static power release from the stored energy in the storage. And in the optimization of the total system, it was also optimized as a balance between the input power from the solar concentrator and the thermal losses from the heat storage, and the compromise being on using a thermal engine or a heat engine that have a higher share of the Carnot efficiency in the net electrical output at higher temperature, but at higher temperature we also release a lot of more heat losses. And in this project we try to figure out the best compromise between these different internal targets. The project also have had a series of evaluations of the safety properties of a system operating at extremely high temperatures, and the properties of how to build a system and make it safe to work on for operators and service and maintenance engineers. Thank you for this, and